This video started off as a quick guide to making a slightly unusual silica gel holder. If that's what you've come for, feel free to jump forward to chapter 7. If I can interest you in a couple of general 3D printing tips first, then bear with me. I've had my 3D printer a little over a year now. I still consider myself very much a novice, but it's proven to be something interesting to learn about and a useful addition to the workshop. There's plenty of scope for fiddling with hardware and software, but for the moment, I'm happy just using it more or less how it came out the box. It's a fascinating process. There's a real danger that if I don't walk away and just leave it running, I could be stood there for hours watching it. One exception to how it came out of the box is this pulley arrangement. I was having great difficulty printing TPU, which, compared to other filaments, is very flexible and stretchy. I traced the problem to the friction between the filament and the path between the reel and the print head. With over a kilogram of force needed to pull the filament through from the reel, it just became stretched until it was tight enough to yank some more through. The solution was to bypass the reverse Bowden and runout sensor. The reel now runs from a ball race sled over the low friction pulley. The difference is night and day. I've tried it with my other filaments too, and it prints just fine, so rather than keep changing things around, I just use the pulley for everything now. The printer lives in an IKEA kitchen cupboard in the garage. This keeps most of the noise and warmth inside when it's running, and it keeps it clear of chips, dust and oil from my other projects. The jury's still out on leaving a 3D printer running unattended. As far as I'm concerned, it's very much a judgment call for the individual user, depending on their own circumstances. In my case, the printer is away from the house and the neighbours, and I rarely ask it to do long or overnight prints, and it's been nailed on reliability-wise. For a bit of added safety, I've added 2 thermal trips that will kill the power if the enclosure temperature climbs to 70 degrees. I have a remote camera with which I can keep an eye on proceedings from pretty much anywhere. And if I spot things starting to spaghettify, it's all powered through a smart plug that allows me to kill the power remotely. Anyhow, the thing I really wanted to share in this video is how I store my filament. The workshop can be pretty damp, especially in winter, and some filament types are known to be hygroscopic. Damp filament can be difficult to print with as it can become brittle, prone to stringing, and flash boiling at the nozzle can leave holes and blobs in the finished part. The relationship between absolute and relative humidity, temperature and filament printability seems to be more of an art than a science. I don't imagine these little low-cost sensors are particularly accurate, but from experience I know that if they say 10%, the filament is plenty dry enough to use. Above that, it may be absolutely fine, but it gives me a clue where to start troubleshooting if a print doesn't go too well. I was given a whole bunch of large silica gel packs. The problem with them is that it's hard to tell when they're exhausted. The moisture the gel absorbs makes it heavier, but when it's in a sealed box, the total weight remains the same. So the only way to check it is to remove it from the box, which is a bit counterproductive as it introduces more moist air. So I bought some indicator gel that turns from orange when fresh to green when saturated. I diluted this with some of the free of charge non-indicator type that I already had. Now this works on the assumption that both types of gel have similar characteristics, and, more by luck than judgment, that seems to be the case. As an aside, blue to pink indicator gel is also available, but this isn't often seen in Europe these days, since the use of cobalt chloride in silica gel was banned after it was identified as a possible carcinogen. That said, I've fond memories of using it to make indicator paper during high school chemistry in the 1980s. I use Lock & Lock 3.9 litre HPL 951 cereal storage boxes. When they say for storing cereal, snacks and more, I don't imagine this is what they had in mind. They fitted all the 1 kilo and under rolls of 1.75mm filament I've used to date. They keep everything clean, tangle-free and out of the way. There's an empty corner at the front which gets a 3D printed holder for a relative humidity sensor. Which also has space for an ID tag. So finally, onto the bit that I've not seen done elsewhere. The Tyvek type material often used in silica gel pouches is permeable, which allows the moisture in, but in my experience it doesn't let it escape very quickly when drying it out for reuse. Plus, putting the pouches in the oven is pushing the temperature limit for the plastic a bit, and because it's opaque, it's not easy to see if the colour has changed from orange to green. The solution I've come up with uses stainless steel fish tank filters from AliExpress. Unlike many of the 3D printed containers I've seen, being all metal means they can easily stand being put in a low oven. The weave of the mesh is open enough to allow moisture both in and out quickly, and although it's easier to see with the naked eye than on camera, the colour change from orange to green is fairly obvious, even through the mesh. The first thing to do is remove the plastic grommet. I'll close the end with an M4x25 stainless steel penny washer. This is held in place with what I'm going to call the crossbar. And this uses an M3 screw to clamp it all together. In the same way that someone might have once said, I think there's a world market for maybe 5 computers, I was certain that my first half dozen gauze holders would be plenty, so the arbor I cobbled together from bits of scrap got recycled. Not long after that I made another dozen, safe in the knowledge that this would definitely cover me. Forever. And so that arbor went in the scrap too. And yet somehow, here I am again. This time I'm going to make a better job of the arbor and hang on to it because, well, never say never. I found a piece of 1-inch mystery steel and reduced the end to 22mm. All the sizes are pretty arbitrary, but I figured making the diameter relate to the size of the crossbars I'd be making later might come in handy. I added a 5mm hole that will be clearance for an M3 tap. Hopefully that'll make more sense later. The other end gets a centre hole for tailstock support and, to hide the head of a caphead screw, a deep counterbore. I reduced the diameter and, using the same logic as before, chose a size that might be a useful reference later on. Regular viewers may recall that I've talked about parting on a mini lathe before. Brass and aluminium are relatively straightforward, but steel can still be a challenge. I'm pleased to say that this mystery metal cuts like butter. The problem here was that I'd not locked off the compound, which was loose enough to allow the tool to dig in. Luckily, I had a spare holder ready to go, and I was able to finish the cut, though I was really careful. Once I'd cleaned up the face, I drilled ready to thread M2.5. Having broken one tool today, I put the tap in my tiny chuck as it limits the torque to finger pressure only. Over on the mill, I cut channels in both ends, and off camera made an end cover from a brass washer. With the arbor finished, I'll quickly run through the plan for the crossbars themselves. I'll start off with an offcut of roughly 1/2 inch by 1/8 inch aluminium strip. I'll spot locations down the length using the DRO on the mill. Half the points will be drilled through 2.5mm to form the centre holes in the crossbars, whilst the remaining spots are there just to mark where I need to cut to separate the pieces. Next, I'll add a radius to the ends, and then cut a rebate on the front edge. There is a little bit more to do, but you'll see that when we get there. So once again, only this time for real, I spotted the locations, drilled through half the points 2.5mm, marked the cut lines, and split the strip into sections. Now this is where the arbor comes in. The separate pieces are loaded on, and then over on the lathe, the corners are knocked off. As the final diameter approaches, I can set the last cut by carefully setting the tool against the wide part of the arbor. Next, the parts are reloaded one at a time. The tool position is set in the same way, only this time using the narrow section of the arbor. A rebate of around 0.5mm is cut. This provides a locating point for the crossbar on the inside end of the gauze tube. The centre hole is threaded M3 over on the mill. And this is where the other end of the arbor comes in. My mini mill doesn't have reverse, so I have to wind them off again by hand. The cone of the countersunk fixing screw stands slightly proud of the stainless steel end cap washer, and to prevent the crossbar from bottoming out, it gets just a tiny chamfer. So, with a bunch of crossbars made, it's just a matter of filling the gauze tubes. I only fill the tubes about 3/4 full, which allows me to see if the colour change has gone right through the whole volume or just at the surface. When silica gel becomes saturated, it can be heated through to drive off the moisture it's collected and then reused. I have a little electric oven in the workshop, and I have been known to secretly use the one in the kitchen too. When drying, hotter is undoubtedly quicker, but overdo it and the colour change will be permanently damaged. The dry gel is a translucent satsuma orange, which changes to a translucent emerald green when saturated. If the gel is overcooked, it takes on more of a muddy brown appearance, and the difference between wet and dry becomes much less pronounced. As the scale on the front appears to be approximate at best, it's definitely worth checking how tightly controlled your oven thermostat is. I let it warm up to around 100 Celsius, but no more. This allows a little for the hysteresis in the thermostat to overshoot without the temperature climbing so high as to cook the silica gel. A bit like barbecuing sausages, the tubes need turning every so often. This distributes the gel beads, but more importantly, opening the door allows the moisture to escape. Keeping the door closed will trap the moisture inside the oven, where it will simply be reabsorbed back onto the gel as it cools. I've enough tubes now to dry a batch at a time and store them until they're needed, so I only need to get the oven out every so often. If this was something I was doing every week, I think I'd come up with some sort of hot air system. Maybe it would have a Peltier element to condense moisture from the incoming air, a fan, a heater, some sensors, possibly a rotisserie for the gauze tubes, and a microcontroller to look after it all. With plenty of other jobs on the list, I think this will remain as just something to think about though. So that's it for this one. Thanks for watching. I hope to see you next time.